Hi everyone, welcome to this online talk on Physics of Language Models, Part 2.1, Grade School Math and the Hidden Reasoning Process. So if you came here from my ICML 2024 tutorial, in that talk I only covered a 20-minute high-level overview of the results, but today I'm going to delve into the details. So motivation. We want to study how language models reason, and there are at least two different perspectives that we can study. One is the behavior process, the other one is the mental process. So to study language models' behavior process, one can imagine that we can design tasks and watch what language models say. You can estimate like the model's correctness and estimate its solution length and solution type and so on. But on the other hand, we can also study the mental process of language models. That is to do probing, to look at the internal states of a language model and discover what their thoughts are and how they actually reason. So you can discover, what planning strategy did it use inside its brain, and did it like trial and error and so on. So in fact, the humankind has studied the behavior and mental processes for almost a century, but not for language models, instead for animals and for humans. For instance, there is the animal behavior science or behavior psychology, and on the other hand, there's also the brain and the cognitive science or cognitive psychology and so on. So if you compare the two words, that is in one word, that is we want to study language models, the other word like to animals, then I claim that it's actually easier to study language models for at least three reasons. Number one, we can take full control of the data. That is, you can control precisely what a language model has seen in its pre-trained dataset and fine-tuned dataset and so on, and then to, for instance, test the models out of distribution, generalization, and so on. But for animals, imagine like if you want to test the monkeys out of distribution generalization to different colors, you have to lock it up like since the first day it was born to make sure it has never seen like the red color and eventually test it on its reactions to the red color. So that's pretty inhumane to do it, and I don't recommend you to do that. So therefore, like it's easier to study language models because we don't have this like humanity issues. The second is that we can do probing. We can actually look inside a language model to look at its different layers at different token positions and what the hidden states actually represent. But in contrast, if you do this for animals, you can only plug in at most maybe 100 different electric probes, and also you don't want to do this like too frequently because it may kill like the animal and so on. And the third thing is that even though training language models can be expensive, but we can pretty much train a very nice language model within a week. And if you train a model that has only, say, 100 million sized number of parameters, then you can train it using a single GPU within a day. But for animals, if you study like rabbits, you can grow only one generation every year. If you study monkeys, it will be multiple years and so on. So for that reason, it's actually easier to study language models. But on the other hand, the reason that we don't really study the mental process of language models is because language models are too capable of doing many different tasks, and it can perform like very complex reasonings. But in contrast, like we typically, when testing animals, we just test it on very simple behaviors and very simple reasoning tasks, such as, I don't know, tic-tac-toe. I saw a YouTube video about a monkey doing tic-tac-toe while I'm preparing the slides. So therefore, like I think language models can study like can perform very hard reasonings. But for us to actually at least do a first step towards understanding how language models reason, let's not use those very complex tasks. Let us say start with an easier goal. That is to study how language models reason on grade school level reasoning tasks. So speaking about grade school level reasoning or grade school level math, then the first data set everyone may think about is the GSM 8K dataset. So this data has only 8,000 math problems. It's nice. It's a nice benchmark. You can apply it on the model that you have trained. But I really don't like it because I don't enjoy it because it's a very small, only 8,000 problems. And typically, even if a model gives a very high score on it, it could be due to data contamination. And for that reason, people have tried to use, for instance, GPT-4 to augment the data by saying that, here are 10 problems and try to generate new math problems in a similar fashion. So you can use GPT-4 to augment, to actually generate almost infinitely many of math problems in this way. But still, the problems you generated may be very biased, and maybe having too few templates, and also the problems you generated in this way are typically also length bounded and so on. So for this reason, we really wish to study reasoning using our own data set. So I will go into the details for how we construct the data in a moment, but at a very high level, if you look at existing math or reasoning data sets for, say, grade school level of math problems, then they have included a lot of things about common sense, such as a candle burns, its length actually shrinks instead of increases, or if you go to work, you earn money, and if you fill a tank, the water level increases, and so on. So there are a lot of such different kinds of and varieties of common senses in which, in order for a model to actually correctly solve the math problem, you have to learn such kind of common sense knowledge from the internet data, from, for instance, the Common Crawl data set. So you have to do that. But as I said, I don't probably want to do that, because if you train a model using the internet data, then you may have the risk of having data contaminations and so on. And also, in order to learn all the common sense that are useful for solving math problems, I suspect that you may need to train really several billion, at least a 7 billion sized model to do that. So that's not super nice. And therefore, we propose to really remove or reduce the common sense in a way that once you build a data set that contains a reduced set of common sense, then you can directly pre-train a model on this data set. So it becomes self-contained, and it becomes much easier to study how the models reason by controlling the pre-trained data set it has seen. So that's the motivation. But although we're reducing the common sense, but we want to capture at least several important aspects that you very often see in grade school level of math problems. For instance, direct dependency that captures, say, if a parameter, say A, that depends on the sum, 5 times the sum of another 2 parameters. So we want to capture this type of dependency. We also want to capture instance dependencies, such as if there are X classrooms and each containing Y bags, then we want the model to be able to understand that there are a total of X times Y bags. And finally, implicit dependency, that is, if Bob has 3 times more fruits than Alice, and Alice has maybe 4X, we want the model to be able to understand that X are not fruits, and so on. So without actually going to the details, let me directly show you one example of what our math problem looks like. So this is an easy example. In this example, the problem description has a number of sentences, and each problem statement actually has an underlying structure graph that defines what are the possible instance parameters that can be that can be covered in this problem. So for instance, this edge here represents the number of film studios in a Riverview High School. So this is a parameter that can be assigned with some value and so on. So this is what we call instance parameter. Each edge in the structure graph represents an instance parameter. And there are also abstract parameters, such as the number of bags inside the central high school. So in this structure graph, the first row are high schools, the second row are classrooms, the third row captures bags. So therefore, if you say how many backpacks are there in the central high school, then this is the quantity that has been asked. So this is what we call the abstract parameters. So abstract parameters cannot be assigned to a value because its value is implicitly defined by the underlying structure graph of the problem. So each sentence now of the problem statement basically captures basically assigns one value. For instance, the Riverview's High School's film studio, this is an instance parameter, and the first sentence just say that this instance parameter is 5 times as much as the sum of these two. So therefore, if you draw the dependency graph, that's a DAG, that's a directed acyclic graph that captures basically what parameter depends on what parameter. And let me actually now show you an example of the solution. So I'm going with you very carefully about how the solution is constructed, and at that point, I think you will understand like how our problem, what our problem means, and so on. So to begin with, the problem is asking for how many backpacks are there in the central high school, right? So that is this abstract parameter. And you need to compute it, but as I mentioned on the previous slide, this equals to the sum of these two parameters. So therefore, you have to compute these two parameters before the question can be answered. And for instance, for this parameter, it equals to the sum of this and that. That is the number of backpacks inside the film studio equals to the number of school day packs and the number of messenger bags inside the film studio. So therefore, the model needs to compute these two first. And for instance, this one, now the problem statement says this is defined to be the sum of this one and that one. So therefore, you have to compute the two yellow ones first. And for this one, for instance, once again, the problem statement may say that this parameter depends on maybe two other things. So you need to compute the two gray ones before the yellow one can be computed. And finally, the two gray ones are already given values in the problem statement. One is 17, the other one is 13. So now you're done. Basically, in the end, you just lay down the computations in the correct order, and eventually you can compute the number of backpacks inside the central high school and therefore answer this question. So throughout this talk, I'm going to use modular 23 arithmetics. The reason is because we want to only focus on reasoning, and therefore we want to reduce the arithmetic difficulties of the problem. I will come back to this point in a few seconds. Okay, so in this way, I have shown you one example of how our math problem is constructed and how its solution looks like. Let me mention a few properties about the dataset. So number one is that we not only look at just those 6 words. So we actually built our own vocabulary that contains about 1,600 parameter names, and that's divided into 4 different categories. Each category has like 4 layers. For instance, in this category, the first layer is high schools, the second layer is classrooms, the third layer is bags, the fourth layer, actually we also have a 4th layer, that is what we call stationaries. So it can be like rulers, pencils, like staplers, and so on, that are things that can be contained inside any of the bags. And then for each problem, we construct a structure graph by randomly selecting maybe at most 4 layers and at most like 16 names from the 1,600 names. And then we construct a structure graph that basically talks about what are the possible objects that can show up in this math problem. And for each problem, we also constructed a random dependency graph. So this is a DAG that captures basically what parameter depends on what other parameters. We made sure there's no cycle, and we made sure each node here has at most in degree of 4, so it can depend on at most 4 different things, and excluding the random number generator. So if it's like if it depends on the random number generator, then there's a number. For instance, this number 5 is randomly generated. And very importantly, in the problem description, we made sure to randomly shuffle all of the sentences, except the last one, which is the question. So this is very important because we do not want the solution to be always in the same order as the problem statement, because if it's in the same order, then all the model needs to do is to just translate every single sentence into the math computation. That would be too easy. So therefore, like, we randomly shuffled the sentences of the problem to make sure that if the model can solve this problem, then it needs to decide what to compute first instead of just following the instructions. So that's an important aspect of our data, that is, we randomly shuffle the sentences here. And another important aspect of the data is that we have a parameter, what we call OP, that controls the number of operations needed in order to solve this problem. So for instance, there are 6 steps here, and one of the steps includes like 2 operations to compute basically the sum of the first 2 and then plus the third one. So therefore, OP equals to 7 for this problem. So we have this parameter OP to control the problem's difficulty. If you compare this to the original GSM-AK dataset, you can see that on one hand, we have greatly enhanced the reasoning difficulty of the problem. That is, for instance, here, like you only saw a very easy example with OP equals to 7, but if you allow OP to go to 21, the problem will be at least quite non-trivial to humans. You need probably 5 minutes or 10 minutes and a scratch paper to solve this problem. So therefore, we have greatly enhanced the reasoning difficulty to make it even more difficult than GSM-AK. But on the other hand, we have also, as I mentioned, removed the common sense from the data. So I acknowledge that common sense is very important. For instance, solving GSM-AK, you need to know that a candle burns, then its length decreases, or if you work for someone, you earn money and so on. But I also believe that it becomes much harder to do a controlled experiment if you want to cover all aspects of common sense over the world. You probably need a very large model and a very long training time to train on the internet data and so on to achieve that. So therefore, like we have intentionally removed the common sense to make the data set self-contained. You can directly train on this data from random initialization without using any internet data, any internet knowledge. The third main difference is that we have actually greatly reduced the arithmetic difficulty of the problem. For instance, whenever you need to add like 3 numbers together, we break it down into binary operations. So this makes the math like much easier. And also like we used only modulo 23 arithmetics. So there are 2 reasons to do that. Number 1 is that we want to make the arithmetic easy so that if a model fails on this task, we want to make sure that it's not due to arithmetics. Because after all, like even memorizing a 23 by 23 multiplication table is just trivial, even for a very small model. So we want to really separate out the reasoning from arithmetics. And for today's talk, actually, you can replace like 23 with, for instance, 2003. Everything will remain to hold, but we choose a smaller number to make it go to extreme, to make sure the math is really, the arithmetics is really easy. So only the reasoning part is hard. And a second reason we choose to do that is because in the end of the day, we probably don't actually want language models to do very hard arithmetics because we have calculators, right? So if by, for instance, doubling the size of a language model, you can suddenly make sure that the model can solve all the 30-digit by 30-digit like multiplications, then is it really worth doing that? Maybe like by invoking a calculator, you can reduce the number of parameters by half, right? Maybe that's even a better choice. So therefore, we do not want to focus on arithmetics. We only want to focus on reasoning in this data set. So the first thing we did using this data set is that we pre-train a language model, a GPT-2, on this data set. So throughout this talk, whenever we say GPT-2, I mean the GPT-2 with rotary embedding. Okay, so we actually trained 100 million parameter sized GPT-2 on this, and this is the so-called GPT-2 small. And we observe how it performs on this data, and we see that the accuracies are already pretty amazing. In contrast, like I will also show you at later of today's talk that if you directly apply this data to GPT-4o and then let it the few shot learn to solve this data, then it pretty much fails like on OP larger than equal to 11. So therefore, this data is not trivial, and the 100 million sized parameter can already solve it to some very good accuracy. So there are actually a few comments I want to make here. Number 1 is that those accuracies are not the answer accuracy. They're not modulo 23 accuracy. So we're not only comparing the numbers. We actually wrote a parser to precisely parse every single sentence of the output. So whenever we say, like, for instance, 99% here or 87% accuracy, we mean the parser accuracy. That is, the answer is actually for every single sentence, every single solution step is correct, including the final answer, and so on. So the second comment I want to make is that we actually made sure that the training set and the test set are completely disjoint. In particular, for instance, during testing, we even tested the model on some problems that are much, much harder than any single problem in the pre-train. In the pre-train, for instance, in the medium data set, the pre-trained data only goes to OP equals to 15. But during testing, we look at the accuracy even for OP up to like 23. And for the hard data, during training, it's limited by 21, but during testing, we actually check the model on even 32 and so on. So therefore, like we call this reasoning length generalization. That is, we really see that the GPT-2 model has the ability of training on some data with certain difficulty and generalizing to problems that require like harder reasoning and more complex reasoning steps. So we see this. And I want to also point out that this is very different from token length generalization. So these days, like people are talking a lot about, for instance, Mamba and rope, especially in the context of how much those models can allow the model to actually token length generalize to problems of longer length and so on. So people study like selective copying or even arithmetics on training a model on certain lengths and testing it on a longer context window. So actually, we are talking about something different here. That is, in this like test set, we actually even made sure that the test problems have roughly the same length comparing to the training data. For instance, in this data, like we're training like with context length window of 124, and during the testing, we made sure that all the problems can be solved within 124 tokens as well. Yet, you still see this like accuracy degrade. That is like if it's in distribution, the accuracy is 99, but if it's out of distribution, the accuracy decreases. So this decrease is really because of the reasoning length generalization. It's not because of the token length generalization. So this is a subtlety that you will see if you look at our paper and so on. But after all, we have seen that the model is capable of out of distribution generalizing to solving harder problems. The final remark I want to make here is that we actually checked and even estimated, how large the data set is. So so this is like one example of the solution, and we actually, for each solution, we converted into a solution template by removing the English and removing the number and making sure the variables are like from A, B, C, like in the increasing order. So after this transition, we counted like, for the problems in the data, then how many solution templates do they share? So for instance, there may be multiple problems, using the same solution template. And then we estimated that the data set here still has like billions or at least trillions number of solution templates. So I hope this gives you a sense about how rich the data is. It's essentially something like the graph isomorphism kind of test and so on. And we estimated that the data is pretty huge. And to this extent, we claim that it just becomes language models can indeed learn the skills to solve these math problems, not just by memorizing the solution templates, because on one hand, there are too many, you can't memorize, and on the other hand, you have never seen a problem of this difficulty length, but they can still solve it. So therefore, like just by looking at this very, very first result, we already see that language models can have this amazing ability of learning the skill to actually solve the problem. So they're actually learning an algorithm instead of memorizing the problems. Okay. And in the rest of the talk, I'm going to actually show you exactly what skills did they develop and how do they solve this problem. So the first thing we claim is that actually GPT-2, after learning on this data, has achieved what we call level 1 reasoning skill. So let me define this. So let us first imagine a level 0 reasoning skill, which brute forcefully computes all the parameters in a maximal kind of fashion. So imagine that, for instance, you go over all the parameters that have appeared in the problem in the order that they have appeared. Then you can go over all of them in this order and try to compute each one of them maximally. So for instance, for the first parameter, you may have found out that it was already defining the problem, so it's already ready. That's 13. And if you look at the second parameter here, you may realize that it's not yet ready for computation. Maybe it depends on something that has not yet been computed, so you skip it. And if you look at the third parameter, you realize that it's already ready. The fourth one maybe not ready, and so on. So after going over this loop maybe a few times, and whenever you hit a parameter that's already ready for computation, you compute it. So this is maybe one reasoning skill that you can imagine. That's what we call the level 0 reasoning skill. And a level 1 reasoning skill will do something smarter. That is, it will do maybe some topological sort to figure out what's the order of the computation, and especially, very importantly, what are the parameters that are not needed towards solving the problem. And then in the end, you only generate the shortest possible solution. So we prepared our data to be of level 1 reasoning. That is, we when giving the problem for the data for the model for training, then we prepared the data so that the solutions are always the shortest. It never computes any unnecessary parameters. And then you pre-train a model. And here is the question: although you get very good accuracies, but did the model actually learn to use level 0 or level 1 reasoning skill? So can the model also output shortest solutions? So it turns out that the model can actually indeed quite well generate shortest solutions. So for instance, this is the table from the paper. We see that the model almost in every 100 problem doesn't generate more than one unnecessary computation. So therefore, the model almost never compute unnecessary parameters. So in the same paper, we also introduced what we call the re-ask distribution. The goal over there is to make the evaluation data distribution to be as far away from the training as well. So only in that example, we see that the model starts to compute some unnecessary parameters, but still very rarely. So in an average of less than one unnecessary computation per problem. So with this in mind, we see that the model is actually quite capable of generating shortest solutions. But if you think about it, this is actually a very non-trivial skill. How is that possible? So it means in particular that before the model starts to say the first sentence, it needs to already mentally process and figure out what are the things that are necessary towards solving the problem. So for instance, there are some parameters that may have already been given predefined values. Those are the leaves in the deck. And it may not necessarily be that all the leaves are necessary towards answering the final question, right? And therefore, before the model starts to say the first sentence, it not only needs to figure out what are the leaves, but it needs to figure out what are the leaves that are also necessary towards solving the problem. So this is non-trivial, right? How could the model achieve this? So in order to answer that, we actually did probing. So we did at least the following 3 kinds of probing. Number one is that we want to understand before the model starts to generate its solution, before even the solution token. At this point, we want to understand after the problem and the question has been raised, then does the model already know if a parameter A is necessary for answering this question? For all the parameters A, does it already know that? And number 2 is that during the in the middle of the solution generation process, say between every pairs of sentences, then does the model know if a parameter A can be computed in the next sentence? Is it already computable? Meaning that is it true that all the parameters it depends on has already been computed? So there's no doubt that the model knows this parameter is ready for computation, but does the model know the entire set of parameters that can be computed next? Okay, so the third thing we try to probe is that even before a question is asked, so at this token position, does the model already know what parameter A depends on what parameter B? So we tried to do this kind of probing in order to understand how the model actually thinks in its internal states. So our technique is what we call the V-probing technique. Let me show you on the next slide. In this V probing, we take a pre-trained language model, which has, for instance, if it's GPT-2 small, it has 12 decoder layers. And this model is capable of, taking a math problem and then predict what is the next token and so on. So we take a pre-trained model and freeze its weights, and then try to do probing out of this. So the first thing we did is to remove the solution, and then replace that with an arbitrary parameter name with a special starting token and special ending token. And now we forward this new input to the model and let it propagate, and eventually we try to read off its last token position of the last layer. So this is the hidden state, and we try to include an additional trainable linear layer on top of that to predict if the parameter A is necessary towards answering this question. So this is the binary classification task. And the dimension of the trainable layer is only 768 by 1, which is a linear layer, and the number 768 comes from the fact that we're using GPT-2 small, so the hidden dimension is of this dimension, 768. And if you just do this, it's called linear probing. That is, you don't change anything and then try to read something off from the last layer. So linear probing is very weak in the sense that, for instance, here we are changing the input distribution. For instance, you're adding this like special starting and ending token. So therefore, like if you directly do linear probing, you can't probe almost anything out of this network. So what we did instead is that what we call the V probing is that we try to also include some trainable changes, but not to the main body of the network, but only to the input layer. That is, remember the input embedding layer is in this case only about 2000 by 768. So because the vocabulary size of our problem is only 2000, because we haven't covered all the English tokens, so we only covered 2000 of that. So then let's do a tiny rank 8 update on top of that. So this is very small. This is only about 1% of the embedding layers parameters, and it's only about 0.02% of all the parameters. And then we train this, not only this additional linear layer on the output, we also train this additional like low rank update on the input layer. And then we try to perform this binary task. So as you see that the entire like network, the 12 layers of the decoders are still frozen. We're not changing anything in between. So here's our concept. That is, we want to train for this new probing task, say this binary classification task of predicting whether or not this parameter A is necessary towards solving the final question, right? We train it once again on problems with operations less than or equal to something, but we test it out of distribution on problems that are much harder and so on. So if the testing accuracy is high for this probing task, then we make a claim. That is, we say that the model has already known this this quantity, whether or not A is necessary mentally at this probing position. Okay, so this is our main concept. That is, whenever this probing is successful, then we said the model has already known this quantity at this token position. Okay, so the reason we want to say this is because we believe that we have, pretty much frozen the entire like network and only added on top of that a very small number of trainable parameters. So therefore, if this testing accuracy is high, it cannot come from the fact that we're training additional parameters. Yes, we're training additional parameters, but very little of that, and only on the input and the output layers. It's like nearly linear probing. Right? And furthermore, that we separated out the training and the test set. So this means that if the model is capable of truly generalizing to those harder problems on this probing task to also predict it with very high accuracy, it means that this knowledge must have come from the pre-trained weights, but not from the newly trainable weights. So that's our main concept. So that was for the necessary task that was here. But if you want to, for instance, probe the dependency task, that is, if you want to decide if the model at this position has already known if a parameter A depends on B, then what you do is to introduce maybe 2 parameters and then again like probe on the last token position on the last layer for a different binary classification task that is whether or not A depends on B, and you check if the model can get good accuracy and so on. So that's how we probe this dependency task. What we discovered in the end is that for all of the 3 probing tasks, the accuracy is actually very, very high, like essentially 99% accuracy, even for the hardest problems that we have tested. So for instance, for the connect probing task, then we tested on the medium and hard data sets, and you see that the accuracies are, even on the hardest problem, it's about 99%. And if you compare this to the majority guess, the baseline, that is, if you always guess, say, no, that the parameter is not ready for computation, then the accuracy is only like about 50-something accuracy. And we also did a very important comparison task, that is to do the linear probing on a random transformer model. And we see that the accuracy is higher than the baseline, but only 60%. So this is very important. That is, during the probing, we have additional trainable parameters, right? And we want to convey the point. That is, the probing accuracy does not come from those additional parameters. And how do you convey this point? One way to do that, we think, is to do the probing from a randomly initialized model directly. This way, like, you can still get some good accuracy. So this is essentially the neural tangent kernel. There's a reason for this. Random model is not totally useless. Like they can still serve as a random tangent kernel, so that if you use the random kernel to try to do the probing, you can still get some non-trivial accuracies. But this is like much, much lower than the accuracies you can get from a really pre-trained model. So in this way, we convey the point that is this probing accuracy actually mostly come from the pre-trained model weights. So this is like for the connect task. And in the paper, we not only did the 3 probing tasks, we actually did 3 more, and we see high accuracies for all of them. So one thing I need to point out is that for some of the probing tasks, especially say the dependency probing task, this is actually a very unbiased task because you can guess no and you get like a probing accuracy of more than 80%. So that's because if you randomly pick 2 vertices in a random graph, then say A and B, then in most cases A doesn't depend on B, right? So therefore, like, to make this result as scientific as possible, we also looked at the precision and recall. For instance, for the dependency task, we also tested what is the accuracy among the positive labels and negative labels, and we showed the accuracy remains to be very high. So therefore, like, we tried to make our probing as scientific as possible, and eventually derived the conclusion that is the model, for instance, for these 3 tasks have achieved like nearly 99% probing accuracy. And we use that to actually explain that how GPT-2 achieves level 1 reasoning. That is how it generates shortest solutions. So for instance, because the model has already known what are the parameters that are necessary, and because the parameter at every single step of the solution generation knows what are the parameters that are ready for computation, then the model can just take a logic n of between the 2, and in this way, it's always going to generate shortest solutions. So that's how we use probing to explain how GPT-2 achieves level 1 reasoning. So a few remarks. That is, we have introduced this V probing technique, right? And I actually spent 10 minutes, actually a lot of efforts in the paper, to make sure that the probing makes sense. So we did many things. Number one is that we made sure that the probing training, for the probing task, the training and test data sets are still disjoint. So for instance, we did the probing training for problems of smaller number of OP, but during testing, we tested for higher OP and so on. So that's one thing we did. And another thing we did is that we tried to make sure that the trainable parameters is very few and also nearly linear. So we only made changes to the output and the input layer, and keeping the majority of the model weights, especially for the 12 layers of the transformer, unchanged. And number 3 is that we made sure actually probing doesn't work on randomly initialized models. So that's, as I said, very important, because during the probing you have additional trainable parameters, and you can actually learn something even using a randomly initialized model. So that's the so-called neural tangent kernel, if you know that field. So you can still probe something. So we want to make sure that the probing accuracy is very low if you do it this way. So that's a very good comparison task to make sure that your probing accuracy mostly come from the pre-trained weights, but not from the probing parameters. And finally, some of the probing tasks are biased, like the dependency task. So we made sure that we also checked both sides of the accuracy, the precision and recall. So both of them are high. So only in that case, we say that this probing is very successful. So the model already knows all of this, at this token position and so on. So that's a quick summary of our V probing technique. So the immediate next result you can read off from the probing is that actually the high accuracy here, the 99%, actually holds for also unnecessary parameters. So for instance, for the connect task, we actually condition on those parameters A that are unnecessary towards answering the final question. And if you check both negative and positive labels, you see that the probing accuracy remains to be very high, in many cases, even more than 99% accuracy. So not only for that, also for the dependency task, the probing accuracy is also very high among the unnecessary parameters. So this is a very important property because it implies, for instance, at this position, an all-pair dependency graph between every pairs of parameters, even before a question is asked. So if you think about it, this is a very non-trivial skill because at this token position, the model does not know the problem has finished. So therefore, there could be some future sentences and so on, but the model has already known what depends on what. And when a next sentence is received, if it, for instance, connects some connected component of the graph with another connected component, the model has to suddenly, within that single sentence, understand what this incremental sentence means and completely update its all-pair dependency graph. So this is a very non-trivial skill that is definitely not needed for solving our math problem. And it's also very different from how humans do reasoning. So for humans, we typically wait until a question is raised, and then we start from the question to backwardly identify what are the necessary parameters needed for solving this problem. So we typically even overlook those parameters. If I give you this math problem, you probably even overlook what are the unnecessary parameters. You probably never even read them because they are not needed. So we actually call this a level 2 reasoning skill. That is, the model actually does this kind of all-pair dependency graph before a question is raised. So we actually view this as a preliminary signal for where this letter G from AGI may actually come from, because the model, we definitely did not provide the model the labels for this skill, but the model somehow developed the skill on its own, and this skill is not needed and is not taught in the pre-training dataset. And on the other hand, this skill is very important because it means the model, after just seeing a bunch of say causal relationships between objects, it actually has the ability to sort out the entire relationship graph between those objects. So this is definitely a skill that can be later fine-tuned for other tasks and so on. But the model can just learn this skill from the math problems that the math dataset that we designed. So you find this already pretty amazing, and we call it a level 2 reasoning skill. So not to mean that it's more advanced than humans, but just to mean that it's has definitely learned and pre-processed things in a very different way from humans, and it pre-processed more information comparing to humans. So let me summarize the talk so far. So I told you basically we constructed a new data set, and in some sense infinite data set, so that you can, number one, pre-train a model directly on this data set, and number two, that the data set is very controllable so that you can probe into the model's hidden states very easily because you have full control of the data. And the second set of results that I showed you, language models exhibit a level 1 reasoning skill and also secretly learned a level 2 reasoning skill. So the experiments in the talk and in the paper, you will see that it's only for GPT-2 small, the model, but actually we tested it briefly like for other architectures like the Llama and so on, and we did not see any difference in the results, so we didn't present that. And in the next result I'm going to show you is regarding how language models actually make reasoning mistakes. So how do they make reasoning mistakes on this data set that we constructed? So if you look at the GPT-2 that we pre-trained, we claim that more than 99% of the chance if it makes a mistake, it has to be one of the following two types. Number one is that it occasionally computes a parameter that is unnecessary. So I said the model almost never make unnecessary computations, but you can always make the test the problem like as hard as possible and as like different from the training as possible. You can eventually make this behavior to show up. But this is only a warning, like because even if a model does some unnecessary computation, it doesn't mean that it's inaccurate. So therefore, like the other type of mistake that is more like an error, the previous one is like a warning, is that the model may sometimes try to generate and try to define a parameter, but the parameter is not actually ready for computation. And then the model starts to basically hallucinate from this point on, because like it depends on something that's not yet computable. So therefore, like it just cannot generate to give a correct solution. So in fact, we checked our pre-trained GPT-2 and we saw these two types of mistakes. And we also checked for GPT-4 and 4.0. I actually showed you a few slides ago that is we did a few short learning using our data set and applied it to GPT-4 and 4.0 and check like how they perform. And we saw like it performs very badly on this data set for GPT-4.0. And in particular, we also discovered that the GPT-4 also make these two types of mistakes. So let me give you one example. That is, we take, for instance, OP equals to 10. And we actually, before we apply the problem, before we give the problem to GPT-4, we actually first provided a very detailed system message. For instance, we told GPT-4 that is, we are only considering calculations modulo 5, not even modulo 23. We made it even simpler, like modulo 5. We also give some examples to make sure the model knows that we're doing modulo 5 arithmetics. And we also restricted our English to only like a specific category, that is school classrooms and backpacks and stationaries. We made it as simple as possible. We even looked at only 16, a maximum of 16 English parameters. You remember we had like 1600, but we actually reduced the vocabulary to be much, much smaller before we passed the problem to GPT-4. And also like before we passed the specific problem to GPT-4, we also told GPT-4 exactly like for this specific problem, what are the high schools that we are considering, what are the classrooms we're considering, and so on. So basically, we're helping the model as much as we can to tell the model about our background to make sure that it understands what are the basic concepts that are needed in order to solve this problem. And on top of that, we also give like 5 short examples to the model and let the model generate, right? So we discovered that GPT-4 also makes the two types of mistakes. That is, it sometimes computes something that's not necessary, and sometimes it starts to compute an instance that is not yet ready for computation. So therefore, we discover also GPT-4 make this type of mistakes. And this is actually a point that I can tell you that why we claim the GPT-4 or 4.0 fails for OP larger than or equal to 9 or 11 respectively. That's because we actually applied our data set directly to GPT-4 with this kind of 5 short learning. And here, like, we only verify the answer, so it's not partial accuracy, it's just the answer accuracy. And if you guess 0, remember, like, it's modulo 5, right? If you always guess 0, you can already get like a 30-something% accuracy. But you see that GPT-4 is pretty much like random guess up to this point of OP equals to 9 or 11, respectively. It's just like random guess. So therefore, like, that was how we claim that GPT-4 fails for OP larger than or equal to this threshold. But in any case, it's not important like how large the OP they can solve, but it's important to see that GPT-4 also fails because of these two mistakes. So this makes it very important to study why the models make these two types of mistakes. So let us look at the first type of mistake, and let's recall that the model actually, before it generates solution, our probing technique shows that the model has already mentally computed what are the parameters that are necessary towards answering the question. So therefore, like you can check the correlation between what the models mentally think versus what the model actually eventually say. And we actually saw a very large correlation between the two. Namely, like if the model wrongly calculated necessary for some parameter being true during the planning stage, that is before the model even opens its mouth, if it already has made this mistake, then we discovered that the model will very likely say that in its final generated solution. And the correlation is about 80%. That is, among those like cases when the model generates a solution step that is not necessary, we saw that the probing accuracy was only about 20% accurate during the planning stage. So therefore, we see that this type of mistake is systematic. That is, you can detect such kind of mistakes before the model even opens its mouth using probing. And therefore, like such mistakes are systematic and they're not really random due to the generation process. You can already detect it long before the mistake is made. Okay, so this type of mistake can happen not only in step 2, but also maybe sometimes in step 15. But even long before that, before the model starts to generate the first token, you can already detect that this mistake is very likely going to be made. So this explains how the first type of mistake is made. Let us now move to the second type of mistake. That is when the model spells out, starts to compute a quantity that is not yet ready for computation. So we actually did similar thing and discovered that if the model actually wrongly calculated one of its parameters being like ready to compute, but actually it's not, then in this case, the model will likely say it in the next sentence. So we again check the correlation between when the model makes mistake versus it does not, and we check that there's a gap between the probing accuracies. So this actually means that to improve the model's reasoning accuracy, it's very important to improve its connext accuracy. That is, it needs to know better for what parameters that are necessary, that are ready for computation and so on. So actually, we spent an entire like part 2.2 paper to study how to improve this accuracy and then in turn improve the model's reasoning accuracy. So that I will cover in a talk that will appear like later next week. So the next result I want to show you is regarding scaling laws. That is, we saw the original scaling law from OpenAI that says, the network width or depth really doesn't matter. And also, like in our prior work in part 3.3, we explained that we discovered that for knowledge scales, only model size matters. As long as you have like a transformer with 2 layers, that's actually enough for you to memorize factual knowledge. But in today's talk, I'm going to tell you that depth also matters. Depth actually matters for reasoning. So here is the experiment we did. So we compiled like 5 different model depths and versus like 2 different model sizes. And for instance, if it's like a 12 layer and 12 head and each head having like 64 dimensions, that is GPT too small. But here, like vertically, we actually tuned the number of heads in a way so that the models vertically in these 5 cases are roughly of the same size. And the models of these cases are also roughly of the same size and twice as large as the size 1. Okay, so we compiled 10 different models. For each model, we pre-trained twice and then took the maximum for the accuracies and evaluated them like with all different OP sizes and number of OPs and so on. So here's what we discovered. We discovered that the testing accuracy has a very clear pattern when the number of layers increase, and it seems not to be very dependent on this on the width of the model in this range of parameters. For instance, if you compare these 2 positions, in the first case, the model is twice larger, of smaller depth. In the second case, the model is twice like smaller and of a larger depth. And you see like clearly in this case, you can get a 94% accuracy, but this case only 60-something% accuracy. So this is actually some very preliminary evidence that is model depth is very important for reasoning. So of course, we only compiled like 10 models, right? And if you want a more comprehensive experiment, you need to do like more models of larger sizes and so on. So we may do it in a future date. But today, I'm going to tell you that is we spend the GPU resources actually to do some probing to further like investigate into why this kind of phenomenon happens. So we checked the probing accuracy with respect to a parameter t at different layers of the network. And here, the parameter t captures the distance of a parameter to the question. So for instance, if the question depends directly on some parameter a, then we say that the a's distance to the question is 1. But if the question depends on a and a depends on b, then we say that b's distance to the question is 2, and so on. So therefore, we plotted actually the probing accuracy of this necessary probing for parameters with respect to their different distances to the question. And we checked, so this is the experiment for a 20-layer neural network, for a 20-layer transformer. And we checked for each layer, then what is the probing accuracy with respect to parameters of different distances to the question. And we discovered two things. Number one is that the accuracy generally like decreases for parameters that are further away from the question. So those are the parameters that in order for you to decide that they're necessary towards answering the question, you need more mental computational steps, because you need to maybe, if t is 8, you need to do at least 8 different mental steps in order to conclude that the question depends on this parameter. And we discovered that the accuracy generally just decreases because it's much harder to determine that those parameters are necessary towards answering the question. But at the same time, we also discovered that the model employs this kind of layer by layer reasoning. That is, generally speaking, like the more layers, the better. So if you have, for instance, like 20 layers, then you see that the model is capable of almost averagely distributing the difficulty of computing those necessary parameters into their layers, and make sure like the shallower layers try to tackle maybe easier parameters, and the deeper layers tackle like harder parameters, and so on. So that is what we discovered, and we use this to actually explain why maybe the more layers, the better. That's because of the model needs to mentally do this very complex operations, and it requires a large number of layers. So a disclaimer, that is, I'm not saying that each mental step requires 1 layer. I'm not saying this, because a 1-layer transformer is Turing complete. It can compute everything, right? For instance, at a single token position, you can use the attention mechanism to retrieve everything to your current position. And then because you have MLP, that's a 2-layer network, you can compute, it's Turing complete. You can compute any function. So I'm not saying that. What I'm saying is that if you have like a 1 single layer, then although this is computable, but it requires maybe your hidden dimension to be very high, and it requires your training to be very low. So what I'm saying is instead, that is within a reasonable range. For instance, in this experiment, when you're restricting the total size of the GPT-2 of the transformer, and if you're comparing against models like when they were trained for the same amount of time, then you see this pattern. Okay, so this is how we make this conclusion, that is, we think depth is necessary for reasoning, and the reason is because of the mental computational step. So for instance, if you compile that to knowledge, then for memorizing factual knowledge, you don't need a lot of like mental computational steps. You just need to recall one thing. But here, like when doing this kind of reasoning tasks, because you have to pre-compute what are the parameters that are necessary towards answering the question, this requires maybe t number of mental steps. And because of that, you need depth. And that's how we so we use this to actually explain like why depth is necessary for reasoning. And the final remark I want to make here is that this phenomenon cannot be mitigated using COT. So we have already used COT. So we're not asking the model to directly answer the math question. We are asking it to solve the problem step by step. But I claim that even for the model to determine what is the first COT step, this already requires some mental computation that is maybe not a single step, but requires multiple steps. So therefore, it's this like mental process, that's the planning stage of even deciding the first COT step, that requires steps. And it's because of this, then we eventually need a deep transformer in order to perform maybe much harder tasks and so on. So that concludes our part 8. So to sum up, in the 3 results here, I showed you like how language models make reasoning mistakes, and it's strongly correlated with the probing, with like how the model mentally thinks about things. And it's because the probing was wrong, and the probing reveals that the language model were thinking something wrong, and that's why like they make reasoning mistakes. And in the final set of results, I showed you like depth matters for long reasoning tasks, and that's really because of the mental pre-computation thing that requires steps. It requires like a multi-step mental computation, and that requires steps. So finally, let me just thank my wonderful co-authors. So Tian Ye is a grad student from CMU, who is my intern, and Zicheng Xu is my colleague at Meta, and Yuanzhi Li is a professor at MBZ UAI, and that's me. Thank you so much for your attention. See you next time.